today we're going to have a look at the electromechanical dynamic cyclic shear machine from GDS. We'll briefly go through the transducers and connection of all of the cables on the system, starting with the axial load cell, which sits right over here on the vertical carriage. That one is color-coded with the black limo sleeve, and the colors match the colors on the dynamic acquisition box, and the axial load will be on channel 0. Then the second transducer will be the main shear load cell, which sits right over here. This is the load cell that directly measures the shear force on the sample without picking up any of the friction inside in the machine. It is color-coded with brown limo sleeve and will connect to channel number 1. The third transducer will be the secondary shear load cell that measures the force on the horizontal carriage, and it sits right over there inside of the machine in the back. So that's the load cell over here. It also measures the shear force, but this one will measure also the friction in the horizontal carriage. And that one will be denoted with the red limo sleeve. So you can plug it to the channel number 2. The next transducers will be all of the displacement transducers. So we'll start with the first one, which is the long-range axial displacement, which is right over here. So that's the transducer that's typically used for positioning in the older systems. In the new system, we also have the motor feedback, which is most commonly now used to just position the system and for the sample preparation. That one will be with the yellow limo sleeve. The next in line will be the axial displacement transducer that will actually be used for the test. So that's plus minus 2.5 millimeter transducer, 5 millimeters total range, which typically is enough in terms of consolidation for most of the samples. That one is on this side over here. So that's the axial LVDT. And this one will be with the green sleeve, but because that's an LVDT, it needs to go through the additional LVDT box, which contains the amplifiers and signal conditioning for the LVDTs. That's why we have the additional cable, which will plug to the channel number 5 and then to the LVDT box. So it's just a short connection cable, making sure that the AC current is changed into DC current for the box to measure it, and then the LVDT itself connects directly to the LVDT box. The last transducer in the typical setup would be the horizontal LVDT, which is right over here. So that measures the shear strain on the sample, and that one will use the gray limo sleeve. So the same way as with the axial LVDT, we plug the transducer directly to the box, and then we use the short linking cable to connect it to our data acquisition. Okay, so once we have all of the transducers connected on the front of the acquisition box, we can start making connection on the back for the mains electrical power and all of the control cables between the machine and the actual acquisition box. So we'll start by plugging 2 mains cables to our 2 boxes. So the system will be typically supplied with a UK type plug multi-block and with the isolating transformer, because all of the equipment that's connected needs to be isolated for noise protection. The transformer itself will come with a local plug to the local electrical standards, so it can plug directly into the wall socket, and then rest will be done in UK style plugs, just to make sure no one plugs any unnecessary devices into our system. So once we have the mains power connected, we can connect the two control cables to the box. Please make sure the blue digital cable goes to CAN open socket, and then the quadrature feedback, which is 9-pin serial connector, will go to the appropriately labeled. Then we just plug the USB cable and plug it to our PC. On the machine side, we have the same cables, so we plug our quadrature for the shear axis, because that is the main axis in that machine. As you can see, the axial axis is blanked off, and two programming ports for the drives are also blanked off, because we only use them during the machine commissioning and testing. Can plug the CAN open cable, and the last part is plug the mains cable. Now that we have all of the cables connected, the last step would be to connect all of the earthing cables, just to make sure that all of the machines are connected to the same ground. So the machine will be supplied with 3 cables like this. First start with the short link. We'll grab one of the longer cables and connect those two over here. Please make sure when you connect the grounding cables, they're done in a chain to avoid unnecessary grounding loops. That cable connected to the body of the main machine, and plug around it. The end of our grounding loop will come to a stop on the multi-block. And once we have all of the cables secured, just make sure they don't put any strain, and tighten all of the nuts, make sure there's a good connection. And the last part. Okay, so now that we have all of the cable connections done, and the machine has all of the power set up, we can turn on the power of the machine. Before you do that, please make sure the emergency stop is pressed in. And now we can start flipping the power switches. on the machine. And we can move on to GDS Lab, start our software, and set up the first connections and just check the transducers, making sure everything works and everything we connected is connected as it should. Okay, so now that we have our machine powered on, we can open our software called GDS Lab. When you first load it, you'll see a screen like this. It tells you where to start. So we can go click here to begin, and we can create a station. From the list, we'll see a list of ini files, which are the configuration files that tell the software what hardware to expect and what types of tests will be run. Those files are specific to your machine and will come on a GDS Lab CD or USB memory stick. So at the moment we have only one ini file, so select that and hit OK. The first thing that will pop up is the connection to our acquisition box. As you can see, we have our box already connected via USB, so we can select that and hit OK. So to begin with, we can go to the Management tab and then go to Object Display, which will show all of the transducers and connections. If I hit Read, you'll see that it starts reading numbers. Down at the bottom, we'll still have an error about the abort button being pressed. But at the moment, we only want to check the transducers and make sure everything works before we start moving the machine or running the tests. If I left click on the icon of the box, that will pop up with the device overview window, in which you can see live readings from all of the transducers. And you can see there's a couple of errors about the abort button. The transducer on channel number 3, for example, is not connected. So now we can just do the sanity check on the transducers. We'll begin with the axial load. So you can watch the value on the screen and press on the load cell, on the axial load cell, making sure that the value goes up. Right. Go over here and try to push the carriage up with my hand. I should see a change in the axial load. And if I release it, the load should go back to 0. So we know that the axial load cell is working. So next one would be the horizontal load cell, which is the load cell over here or left. If you look to the side of the load cell, you'll see which way is the positive direction denoted with an arrow. So if I grab the back of the load cell and pull it towards the front of the machine, I should see the load changing to the positive value. And when I release it, it should go back to 0. If I push in front of the load cell, the load go to negative. When I release it, it goes back to 0. So we know our second load cell is working. And so the last of the load cells will be the horizontal load cell, which sits on the back of the machine, as explained earlier. So if you think about the setup, for this load cell to read positive, that load cell will read negative because they are the opposing forces, which means if I push on the load cell, on the carriage, it should start reading positive values. And if I gently pull on the carriage, the values should change to be negative. So those would be the checks on our load cells. To check the displacement transducers, we'll use the motor control because that is the safest way. The motors are set up and communicate with the acquisition system. To do that, we'll release the stop button, which will energize the motors. The machine should not be moving anywhere on its own. If you look at the screen, it tells you what to do. So the machine, because we had the abort button pressed, it saved some errors in the memory. But to clear them, you have to press read twice. And when all of the values turn blue, that means the machine is ready to be moved and to be controlled. I can change the layout from transducer only reading to control parameters, which are the parameters that we ask the machine to control, or I can see all of them on one screen with TX/CP. Click read. My values should be all in blue. And then looking at the control parameters, we have the control of the axial load, axial displacement LVDT, axial displacement encoder, which is the motor feedback, and then horizontal load, horizontal LVDT, and horizontal displacement motor control from the encoder. So open up the axial first and just make sure we can safely move it. So let's say move it down by 1 millimeter in the positive direction. So as you can see, it moved to 1, and we saw the machine moving as well. And double check, move it to 2. So all seems to be in order. So you can move it back to 0. So you can see the machine is moving. So now to just double check the transducers, drop the armature from the vertical LVDT. There's a holding bracket that just slides. It's just spring loaded to the body of the carriage, and then I can move the LVDT down. If you look at the LVDT, you'll see 3 lines that mark the top position, the middle, and the maximum position. So I'll position it somewhere closely to the middle and tighten my screw. So position it somewhere close to the middle and tighten the screw to hold the armature in place. It doesn't need too much force. There's no force going through that armature. It's just to make sure it stays in place during the test. So we can move to our software now. So as you can see, because we're moving the LVDT by hand and we pushed it past its limits, and now we have the error showing up on the screen about the main data channel number 5 being saturated. To clear that, just press read twice, and as you can see, our LVDT is in the reading range, so we're getting a value reading from it. At the moment, we are not setting up the test, so we'll not look at the offsets. We just want to make sure that all of the transducers read similar values. So if we look at 3 transducers that read our displacement, which is axial LVDT, axial displacement encoder, and axial displacement long range, they should all move now by 1 millimeter in the positive direction. So as you can see, they all change by 1 millimeter. We move it 2 millimeters. So it seems like all of our axial displacement transducers are reading correctly. So the last thing to check will be the horizontal displacement transducers. So as you can see, we have the LVDT and the motor encoder. So if I select the encoder control for the horizontal axis, I can target 1 millimeter. And as you can see, both of our transducers moved by 1 millimeter into the positive direction. Target 2 millimeters, you can see that both of the transducers moved by 2 millimeters and return back to 0. Okay, so now with all of our transducers checked and working, the last final check would be to make sure the position of the shear LVDT when showing 0 as the reading will make the top cap and pedestal parallel to each other. To do that, we just need to quickly drop the top cap and the pedestal in the machine. We are not going to be running a test yet, so we just need to tighten them in place. Where they will sit during the final test. And from the software, from the object display, we can go to axial encoder and target the maximum positive position to bring the top cap and the pedestal closer, and then using the horizontal LVDT we target 0 position, which should make the top cap and the pedestal in line and two faces parallel. That's what you're looking for, is for that face over here to be in line. I'm just gonna quickly use one of the discs. So you can see both the top cap and the pedestal are in line. So that would be our sanity check on the machine. You only need to do it when it's first out of the box, just to make sure everything works and everything is connected correctly. When you're running further tests, you don't need to repeat those steps unless machine is moved or something has changed in the setup. So now we can have a look at placing the sample inside of the machine and setting up the actual test on the rubber dummy sample. Please remember that during the actual test, if the temperature control in the laboratory is not very good, ensure that the cover is placed down, which will protect the transducers from any sudden temperature changes, like the AC units kicking in or someone opening up the door or opening up the window in the laboratory. Will ensure better stability of the results and of the transducers. Okay, so now we'll have a quick look at the initial setup of the sample set assembly, including the pedestal and the top cap. So we'll start with bolting the porous discs onto the pedestal. Please make sure that the bolts holding the discs are very tight, because they'll have to carry the shear force on the sample. So you can do the same for the top cap. Now that we have our discs in place, we can put our membrane around the pedestal. Make sure it sits flat against the bottom. And we can place our first O-ring to seal the bottom of the sample. And now, to hold this down, we take one of the bottom holding rings with 3 bolts. And useless. Once we have the bolts in the correct orientation, just tighten them, make sure the O-ring is being held down by the ring. We can place our So now that we have the first O-ring down there, we can place our second O-ring, pull it a bit downwards, making sure our membrane still sits nice and flat against the side of the pedestal. Place our second ring. And tighten it in place. The screws for both of the rings don't need to be super tight, as they're only holding the O-rings down to make sure they're compressed against the membrane and the side of the pedestal. So that would be our typical assembly for all of the types of sample preparation. For more information about different options and different hardware to prepare the sample, please refer to GDS help sheet number 146. Okay, so now that we have prepared our sample, we'll place the sample set inside of the machine, top cap and pedestal. But before we start, we need to move the axial actuator all the way up, so we have enough clearance to safely place the parts inside. So just target -50. The actuator will move up and it will automatically stop on the limit switch. We also need to check, as we did in the previous step, that we are targeting the 0 position on the shear LVDT, because that is the position in which the top cap and the pedestal will be aligned for the test. So our machine is fully up, so we can first place the top cap. I'll put the O-rings on the top caps that we'll then later use to clamp the membrane and place our top cap inside of the machine. So, as you can see, the top cap will lock on the key that is it's in the load cell and it fits the recess in the top cap. When you're placing the top cap, please make sure the flat part is facing to the front, because that will be used as the target for the horizontal LVDT shear upgrade. So I will lift my top cap, make sure it's tight in the key, and then place one bolt to hold it in place. And now this bolt is holding the top cap. We can place the remaining bolts. And tighten the top cap in place. Make sure all of the bolts are nice and tight, to make sure there is no movement of the top cap against the load cell during the shear test. Okay, so the next part would be to place the sample. Try to do it as gently as possible. Make sure you minimize the disturbance to the sample. So drop the whole assembly onto the machine and slide it very gently until it hits and sits nice in the key. And now we can tighten the pedestal down in place. And in the same way as with the top cap, make sure that all of the screws are nice and tight, so there is no movement of the pedestal against the horizontal carriage. Okay, so now we can move to our software. So begin with left clicking on the icon of the box, which will bring up the device overview. From here I can apply the offsets on all of the load cells, because that is our starting position. There is no force from the sample acting on the load cells just yet. So we're setting up our zero references. And then I can move to the docking feature. We'll move down at the speed of 1 millimeter per second, and then we'll consider 0.05 kilonewtons as the docking load, and we want to maintain that force after the sample is docked. All of those parameters can be changed to suit the needs of the testing and the sample. And now I can just click extend. And as you can see, the machine will start moving down until it touches the sample. At this point, it's worth just double checking you are not catching any membrane between the sample and the disc, just to make sure you're docking purely on the sample. And as you can see, the status in the window has changed to dock, which means the machine is now in the control of the load, targeting the constant small docking value. So now we can actually flip the membrane and take off the vacuum former and actually prepare the test. So I'll start with lifting the O-ring, and then I'll Gently flip the membrane and slide it up. So slide the membrane. So we will not be using that O-ring anymore. That was to hold the membrane against the vacuum former. So we can slide the membrane up, pull it gently, and then pull the membrane O-rings down to seal the sample. So now we can take apart our vacuum former and we'll be ready to run a test. So vacuum former will split into two parts. So just undo the bolts. We can move the parts away from the rings. Put our O-ring down. So it's not disturbing the test and our sample. And now we're ready to set up the software. One last thing. This is our starting position. This is where we're docked. So drop the armature, and as we did the last time, I'll try to find the topmost position, because we're gonna be only consolidating our sample. We want the full range of travel going downwards. That's why we're setting the LVDT up in the top position, tightening the screw to hold the armature in place. And the last things to work on will be the software side. So now, because we're basically fully set up, I can move again to the channels and apply offsets on all of my displacements. So I can apply the offset on the long range, on the axial LVDT, on my horizontal encoder, and on my axial encoder. They're all set to 0, and now we're ready to start the test. I'll close the device overview. Because we're moving the LVDT manually, we still have some errors. So before you start the test, make sure that the software, all of the values are red in blue. And as you can see, everything is working fine. So I can close that window and we can move on to setting up the test. Okay, so with our initial setup done, we can move on to setting up a test. Please note that this will be only a general guide, and further information about all of the options you will see in the software can be found in GDS Lab handbook that should be attached on the CD or USB memory stick. So we'll start off by clicking on the Data Save button, which will allow us to choose data file. And for this test, we'll use the single directory. I'll click Next. We'll use the linear saving type, .gds format of the file, and one data saving interval of 1 second. We'll tick the box to save the calculated data, which will save the parameters calculated based on the initial sample size, like strain and stress. Next. In here, we'll specify the location of the file and the name. And we can click OK. Then we can move on to the sample setup. So set up the box samples, and software will pop up with few windows about the questions, asking what's the current state of the sample. There's a test on a new sample, and our sample is docked because we did that during the preparation. So I'll hit OK. We are using a rubber dummy sample, which is cut to the size of the pedestal and to the appropriate height. So we'll leave those two parameters in there as they're set up. On the left-hand side, you can specify all of the information about the sample that will also be saved in the file to help you identify sample post after the test. And we'll go to add the test to the list. So you'll see a number of options, a number of software modules, and for more detailed information, please refer to GDS Lab handbook. Today we're going to use the advanced shear and dynamic shear. We'll start with the advanced shear. So GDS Lab is a stage-by-stage software, which means the whole test is specified in individual stages in which you ask the machine to perform certain tasks, or be it increase the load, target a certain displacements, and or similar. So we will go to create a new stage, which will pop up with a window from the advanced module. In this test, we will first increase the axial load, or our normal stress on the sample. So to do that, I'll control on shear displacement, horizontal displacement 1, which is our LVDT, our primary displacement, and we want that value to be kept at 0, so keeping the constant position while we're increasing the load. And then we'll increase the load, so choose the axial force control. And as you can see, we're currently at our docking load. For this test, increase the target to 2 kilonewtons, and we can hit next. Over here, we have a number of additional options depending on the system. For GDS Electromechanical dynamic simple shear, EMDCSS, those options are not applicable, so we can just click next. And then we can specify the end of the stage conditions and all of those parameters. For this test, we'll just wait for user interaction and we'll move to the next stage manually. However, you can set up the software to run the full test and run all of the stages automatically based on the shown termination or end of the stage options. If any of them will be met, or if any of those conditions will be true, the software will move on to the next stage. So we'll add this test to the list, and now we can go to our test list. As you can see, we have set up the stage 1. So you can modify if you double click, you can still modify the parameters for the stage that is not currently running or it's not finished. Just go click through this next. You can go to the test, which will move us to a different window. If I go test plan, I can still review my plan and my test. At the moment, we have only one stage, and we have set it to move to the next, so to wait for the user interaction before it progresses further, which means we'll be able to just manually stop it. If I double click on the graph, this will pop up with the graph options. And let's say on the first one, we want to see the vertical load, and on the second one, we want to see the axial displacement. So we know when our sample is fully docked, we can go OK, and we can go to start the test. If I change the graph 2, you'll see that my vertical load is increasing. Set it to go to 2 kilonewtons. So as you can see, the software is maintaining the 2 kilonewton docking force. Look at graph number 2, which is our axial displacement. We can also check the value over here. We'll just give it a little bit of time to completely settle at the new stress. Please note that this is a dummy rubber sample, so typically that curve on a real soil would take a bit longer. If you want to change the parameters that are displayed in this section, you can click on Browse Live Data options and just tick parameters you want to see in the numerical values outside of the graph. Click OK. So now with the stage number 1 running, we cannot modify the parameters of that stage anymore, but we can create a new test. There is a number of ways to run a dynamic cyclic, dynamic simple shear test, but today we'll follow the guidelines of setting the shear stress to 0 after the docking, after the normal stress is reached. So we already have our 2 kilonewtons on top of the sample, and we will keep that force. But now in this stage, we'll move the shear force to read 0. So we hit next, and again, we'll wait for user interaction. So add that to the test. As you can see, we have set up a stage number 2, which means now we can move to the stage. So as you can see, the software is plotting the time from the start of the stage. However, if you double click on the graph, you can change that to show all of the data from the start of the test. Now, as you can see, this is plotting the data from both stage 1 and stage 2. So now we'll run a test. So the test we'll run will be a constant volume test, which means we'll hold the axial displacement in place at the force, at the normal force specified for the test, and we'll apply a cyclic loading. Here we'll use the CSR of 0.1, which means our horizontal force will be 10% or 0.1 times the normal force, which will be 0.2 kilonewtons. So now, because we will run a dynamic test or dynamic cyclic simple shear, I'll change to dynamic shear module. and hit on create a new stage. As you can see, for the dynamic module, the window looks a bit different, or it's purposed for the cyclic shear. We'll run a test at 0.1 Hertz. We'll choose our main LVDT for the control, or the LVDT, the 5mm, more accurate LVDT on the side of the machine. And we'll use initial value, which means the software will target the current value of the LVDT, and the amplitude of our sine wave, or the amplitude of the axial displacement, should be kept at 0, because we want to maintain the constant volume of the. In the on the shear axis, we want to do the cyclic loading. We'll start with datum of 0 kilonewtons, which is currently what we have targeted, and we'll use the CSR of 0.1 or 0.2 kilonewtons. We'll put the stiffness estimate as 1. For more information about the stiffness estimate, please refer to the handbook or to our knowledge base. We can click next. We'll run a total of 50 cycles, saving 100 points, 100 data points per cycle. And because it is a rubber sample, we will not specify any of the termination conditions. However, in the real test, you can specify if the software should stop the test when a certain strain limit is detected. And we'll add the test to the list. So before we move to the next stage, we can quickly go to the Management tab, and to Object Display, once again, click on the icon of our box and choose the Dynamic Graphs. So the dynamic graphs will pop up only when we run a dynamic test, but there are certain parameters we may want to see as the live data. Please note that the data from the graphs can be saved manually. However, all of the data is saved as specified in the GDS Lab in the dynamic shear software module. I'll unpick the Axel encoder, so we only want to see the data from those 4 graphs. And now we can close the window, hit the Object Display, and hit see our data is being displayed on the real-time graphs, but at the same time, the data is also being saved into the software. So if I double-click on this, and I change the horizontal displacement versus the horizontal load, you will see that the software will be plotting the data in the graphs to the main window. They don't disappear. I click away. On graph 2, plot the vertical load, horizontal load. As you can see, we are running the test. Just change the graph as well to be horizontal load. change load from the start of the cyclic stage. We have set up a 50 cycles. Of course, you will not see a typical failure or liquefaction from a rubber sample. However, just to show how to set up a test and how to run the fast test, this would be the initial. Okay, so now that our test is done, you could add more stages to the test and run them post-cyclic test. However, we're just gonna quickly have a look how to safely remove the sample from the system and how to take the apart. So to do that, we'll go to Management, Object Display. We'll want to go to the horizontal displacement encoder and click hold position and want to open axial displacement encoder. Load. So now that we're targeting a hold position on the horizontal encoder, we can increase the load to a very small value. Fast, and now that we have dropped the load, we can target a position that is above the sample, so you can safely remove the membrane and remove the pedestal. So I'll send the target to -1 millimeter. As you can see, our axial displacement LVDT went out of range because we moved above the sample. However, at this point, it doesn't matter because we'll be removing the sample from the assembly. So now we can have a look at doing that. Right. Okay, so now with our axial axis positioned above the sample and no forces being in the system, we can safely move the LVDT up and take apart the membrane. So start by undoing the armature on this side, lifting it up and sliding the bracket to hold the armature above the sample and in position just to make sure we don't damage it while we're taking the sample out. So now we can lift the membrane and slide both of the O-rings above the membrane. To get a bit more clearance, we can now go to our software and target the top position for the actuator, just so we have enough clearance on the sample and around the sample to take it apart. The last thing would be to undo all of the bolts on the pedestal so we can remove the sample. And we can safely remove our pedestal and place it on the table. And that would be the end of our initial instruction video, how to run the first test and how to check the machine when it first arrives in your laboratory. Thank you very much.